Hey guys, welcome to day 22, and today we are going to be talking about more data structures, and these are going to be in the form of graphs and trees. And so, no, not bar graphs, but we're going to be making more like tree graphs, hence the trees, the graphs. And it's going to be a lot of notation. And by notation, I mean I'm going to throw a bunch of definitions at you, and you're going to catch on pretty quickly. It's going to be great. And so when you were like in elementary school, middle school, or if you're there now, when you think of a tree, you kind of draw a little stick and a bunch of circles. But we're going to be doing something different here. Here, when we draw a tree, we are going to draw something called a root. And this is just going to be a node. It's going to be an element of our tree. And so a tree is made up of leaves in real life. Like here, our root, it's just our first node here. It's our first leaf. This root is going to have two children, and so if we have this root here, it's like the first element, then it's going to have two children that are like the second and third leaves, the second and third elements here. And so these three nodes, these three pieces make up a tree. These three leaves, that's like with them together, you have something called a tree. The top singular one, again, is called the root of the tree, and then it branches out into the two children. This concept is very, it's notation, root, children, you got it. Now we can add more children to the tree. We could add a child to the left node, we could add a child to the right node, and by node I just mean, the little circular thing. And so here we have our left node, our right node, we can actually add more children to them as well. And so if we add these children, now the middle nodes are called parents, and the bottom level here are called children. Now you might be able to see that this data structure, this tree thing, is a bit recursive because you have this tree. Here we have the three levels. We have the root, and then we have the two children, and then we have like the bottom level of children. And here we have a root and two subtrees. And so the children of like the main root are trees as well. They're not just children, they're actually children trees, subtrees. And each subtree in itself could have like a root and then more children. But they don't have to have children, and those children don't just have to be nodes, they could be subtrees as well. So different organizations of a tree make up different data structures, whether you have like a bunch of children and what demands something be a root, what demands that something is a child, like why would you make one element a root and the other a child? Like what is that relationship? That's what makes different data structures that we can represent. And so one of these data structures is called a heap, and a heap is usually organized so that the root has a special relationship with the children, but the children themselves have no relationship with each other. There are two main types of heaps. A min-heap, which is what we're going to talk about first, has the smallest element at its root, and everything below it is bigger than the root. That's the relationship. The root is smaller than its children, but that does not mean that one child is smaller than like the other child, or they could be equal. Like just because you have a root, say the value of the root is 5, then whatever's below it has to be greater than 5. But the two children that it has could be 10 and 10, they could be 10 and 12, they could be whatever you want. And they could be switched just because that it doesn't matter, the order doesn't matter, they just have to be less than 5. So the children could really be anything as long as they're smaller than the parent. Let's take a look at a real life example. So say that you and your 3 friends, you're going golfing. You really like to golf. You're going golfing and it's great. And you decide to golf 18 holes. At the end, you look at your scores and decide to use a min-heap. I know, just pretend you would actually do this in real life. You would use a min-heap to depict your data. So you want to see like who had the best, score. And in golf, you want to have like the lowest score, because what the score means is how many times you had to hit the ball for the ball to get in the hole. And so when you're golfing, this is life advice here. If you ever go golfing with someone and it's a par 3, you want to try to get your ball in the hole like in less than 3 or at least 3 strokes. You want to hit it 3 times that's like the average, or it's like the good golfer average, and usually people go like 6 strokes, and a stroke is just, hitting the ball. Anyways, enough about golf. We're talking about code. And so you want lower scores in golf. And so you did your golfing and now you're back, and you went on the course with your friends Jake, Alice, and Rebecca. So you are an amazing golfer and finished with 80 strokes, but like your friend Jake, he's not so good. He finished with 120 strokes. Alice with 100 strokes, and then Rebecca with 105. So now that we have this data, we can actually graph it and see, measuring by the strokes, and actually see like who visually looks like they did the best. And so someone that can look at the graph and see very visually like, oh, this person was the best, oh, this person was the best, etc. And so according to our definition, the root of the tree should be the minimum of the rest of the heap. So our first node, our root will be you. And so you got 80 strokes and it's great, and so you're the root node. Now below you, you have two children, Alice with 100 strokes and Rebecca with 105 strokes. And so you could say, have them next. Last, we have Jake. Jake isn't so good at golf, as we said before, so he's at the bottom of the tree. Now, which node does he go under, Alice or Rebecca? Well, it doesn't matter. All our min-heap rule says is that he must be greater than whatever he goes under. So since 120 is greater than 105 and 100, he can go under either Alice or Rebecca. Both, trees are equal representations of the data. We can also switch around Alice and Rebecca because Alice and Rebecca have no correlation to each other. In fact, we could reorganize the tree so that the two direct children were Alice and Jake, and Rebecca wasn't a child of Alice. However, if we reorganize the tree like this, then Rebecca could not be a child of Jake because Jake has 120 strokes, and that is greater than Rebecca's 105 strokes. This min-heap rule, where the root has to be less than the children, remains true through the rest, throughout the entire tree. And so it is quite recursive as well in structure. Here, our core tree, you, Alice, and Jake, you have a lesser score than Alice and Jake, and so that's why you're the root of the tree. And then for Alice's children and for Jake's children, they are going to be in that same ordering as well. And so as long as that property is held at every single level, you're never going to have a chance of something bigger being on top of something smaller, because that's not what the min-heap rule does. Lots of words. Okay, so our next type of heap is a max heap, which is a bit of the opposite of a min-heap, but it's very, very similar. And so a max heap has the largest element as its root, and everything below the root is smaller than the root. And so it's the opposite. On the min-heap, the root was the smallest element. In a max heap, the root is the largest element. Some of you may know me and go to Vassar, and if you've ever been to Vassar in New York, then you know that the squirrels here are crazy. They are not normal squirrels. Now, why am I talking about this? Basically, these squirrels, they race around Vassar like they own it, and they look at you like you're crazy, and they rule the world, they prance, they're the life of the party. These squirrels are insane. And so I imagine that these squirrels they're pretty smart. And so we could compare how many acorns they get, and I bet they, go back to their little tree huts or wherever they live, and there's probably a squirrel master overlord that has collected, the most acorns. And so they want to see, who is the real deal. They could have this long list of how many acorns everyone's collected, but in a tree they would be very easy. It'd be very easy to see, okay, this guy's on top, he's collected the most. So say we get some data and we get to enter, the squirrel home, and we find out that squirrel 1 collected 5 acorns, squirrel 2 collected 8 acorns, squirrel 3 collected 10 acorns, squirrel 4, 3 acorns, and then squirrel 5 acorns. And we can graph it to make it something like this. It's the same type of ideology as the min-heap, so we can switch things around and have multiple representations of this data as long as the max heap property is preserved. And basically that just means the root, anything that's higher in the tree should be greater than anything that's lower in the tree. Now, there's one thing we haven't talked about yet, and that's how this tree, heap idea can be implemented as an array. So here, when I'm talking about our arrays, we're going to actually start our indexing at 1 rather than 0, because it's going to make a little bit more sense. And you usually do this when you're working with algorithms and stuff like that, and algorithms are just methods, but yeah, so we're starting our indexing at 1. And we are going to add a bit more data to fill up our heap so that each node either has no children or 2 children, just to, clean it up a bit. And here we are. Now we have a heap containing the number of acorns different squirrels have. However, in this graph, I've just written the number of acorns that squirrels have collected throughout the years, so we can look at it a little bit more clearly without all of this squirrel labeling. So to turn our acorn heap into an array, we have to number each node. How do we do this? Well, our top number is 10, so we'll label that 1. Then have the children 8 and 5 beneath it, numbered 2 and 3. Then node 8 has a 5-child and a 4-child beneath it, which will be numbered 4 and 5 respectively. Last, our node 5 on the second level has 2 children, 3 and 1, which will be also labeled 6 and 7 respectively. Now we have our numbers. How can we make this into something we can mess with, an array? Well, we can draw it out and see what happens when we line up the indices with their numberings. The 1 lines up with the 10, the 2 lines up with the 8, 3 with the 5, you get it. And so we have some cool things we can do here. To get the child of the first node, so we can still represent the idea of parent and child inside of this array. So to get the child of the first node, we can just take its index, 1, and then multiply it by 2 to get one child, and then add 1 to get its second child. So if we multiply 1 by 2, we get 2, and at index 2, we have the node 8, which is in fact a child of 10. If we add 1 to 2, we get 3, and at index 3, we have the 5 node, which is also a child of 10. We can do this to find the children of any node in the tree or here array. In addition, we can use indexing to find the parent as well. If we take the node at the 6th index, we get the node with a value of 3. To find this node's parent, we can then take this index 6 and divide by 2. When we divide by 2, we get 3, and the node at index 3 in this array is a node with the value of 5. So the node at index 3 is the parent of the node at index 6, and we can do this to find the parent of any node here. Now there's a bunch of other things you can say about heaps, like functions to make heaps from a set of data, or to reheapify the data when you want to, insert thing, but we're not going to talk about those now. I'll leave links down below in case you're interested, but we are going to move on to a bigger topic, and that is binary search trees. In our heaps, we didn't have to worry about any of relationships between our children. They were just less or greater than the root depending on the type of heap, min or max. However, for a binary search tree, which sounds really scary and intimidating, we will have to worry about this relationship between the children. What is a binary search tree? Well, it can also be called a BST, and it's a tree where the root is like the middle node, and the left child is less than the root, and the right child is greater than the root. So if we have the nodes 7, 8, 9, we would organize it like this, where the node with the value of 8 is the root, the left child is 7, and the right child is 9. Makes sense? And this will continue down the tree just like our heaps. So if I add 5, then we have the same tree, but 7 now has a left child of 5, because 5 is less than 7, but then it is also less than 8, so that's why this works here. Like our heaps, BSTs can be implemented as arrays as well. If we number our nodes, 8 labeled as 1, 7 is 2, 9 is 3, and 5 is 4, we can create an array. At slot 1, we have 8, slot 2, 7, slot 3, 9, and slot 4, 5. To find the parent of a node, say the node at index 4, we can divide 4 by 2 to get index 2, and at index 2, we have the node 7, which is in fact the parent of the node 5. To find the left child of a node, we simply multiply the index of the parent by 2 to get it. Similarly, to find the right child, we multiply the index of the parent by 2 and add 1 to get that node. So much talking. Okay, we are actually going to program a binary search tree. This thing that sounds so intimidating, we're actually going to make it right now. And so to do this, we are going to open NetBeans here, and it's going to pop open for us, and we're actually going to implement a binary search tree, which is going to be great. And so the first thing that we are going to do is create a new project here. We will go new project, and we are going to call this a new Java application, and we will say binary search tree is what we're calling this, and there we go. And with this file, the first thing we're going to do is create a tree interface. And so this is going to be kind of weird. We haven't really done this type of stuff before, but you're going to get it. You understand interfaces, I think you're going to get it. So basically, the reason we're going to have an interface is because we're going to have two types of classes. We're going to have, of course, our interface, and then with that, we're going to have two classes that implement this interface. One class will be a non-empty BST, a non-empty binary search tree, and the other class will be an empty binary search tree. So we're going to have two classes to kind of represent our binary search tree, one that is empty and one that is non-empty. Make sense? And so basically what's going to happen is this interface is going to have methods that we want to call on a binary search tree. So say add, member, is empty, stuff like that. And if you don't know what those mean, that's fine. We will talk about them because we're actually going to program them. But basically, no matter what, if I'm working with an empty BST or a non-empty BST, we are going to want to call these methods on them, and we're going to want them to have implementations. And so we are going to do new Java interface, and we are going to call this interface tree just because, it's a tree. And here inside of our tree, we are going to write some signatures. And the first signature we're going to write is public boolean is empty. And it's just going to have no parameters. We're going to see, is the tree empty? And then if it's a non-empty tree, we'll say false. If it's an empty tree, we'll say true. And then we're going to add another method that's public int cardinality. And that's just going to be like the size of the tree. If it's an empty tree, we'll say 0. If it is a non-empty tree, then, we'll say however big it is. And we'll program that later. And it's going to use recursion, which is exciting. And then we are going to write public boolean member. What is going to be in our tree? Is it going to be ints? Is it going to be strings? What if we don't know? We can make this generic. And so we want to say type D element. Now it's going to error because it doesn't know what D is, and so we need to put something here. But do we want anything inside of this binary search tree? Well, no. In a binary search tree, you have the root, which is kind of like the middle node. Anything on the left is going to be less than, the thing in the middle, and anything on the right is going to be greater than, the root. So we really need our data that we're going to be inserting in here to be comparable. We need to be able to say, okay, this instance is greater than, equal to, or less than this other instance. So really our D here needs to extend comparable, because otherwise, and we need to say extends, keywords here, and it needs to be comparable because we need to be able to say, okay, is string A greater than or less than string B, and if so, where do I put it in the tree? And the last method we are going to add to this binary search tree is going to be a public non-empty BST that is going to hold type D, and we're going to add our D element. And so basically what this says is that I'm going to create a non-empty binary search tree when I add something. And we know we can return a non-empty BST because when you add something, there's no way that your tree can be empty. And so here it's going to be mad because we need to create a class. And so we're going to choose this first one. And there we go. And now we have this non-empty BST. But of course, we should probably do our base case, the empty BST, before we move on to this guy. So this guy's going to be here. But don't worry, we will come back to it. And we're going to add another Java class that's going to be empty BST here. And it's this new class, and we're opening it, and here it is. So what are we going to write in here? Well, the first thing we need to say is implements tree with type D, because we know we wanted to implement our interface, and we know inside of our tree we wanted to have this D. We want it to be that data type that it is asking like to be a member of, and that it returns full of if we add something. And so we're going to have some errors, and that's because we need to add D here. But we're still going to have an error, and it's going to be this famous error that I have dealt with for so long. And so basically here we also need to say that D extends comparable, because inside of here D must be comparable, and in here we need it like at all instances. If it's in the BST, then it's in the tree, and if it's in the tree, then it needs to be comparable. And so now it's going to error because we don't have implementations for some of these methods, but we're going to create a constructor and it's going to be great. And so inside of our public empty BST constructor, we're actually not going to do anything. We're going to have no fields. It's weird, but that's what's happening here. And so the things we need to implement, well, is empty. So we'll do public boolean is empty, and we're going to return true because if it's an empty BST, it's true. Then we're going to have public int cardinality, open close parentheses, open close curly brackets. And here we're going to just return 0 because if it's empty, there's nothing inside of it. So the cardinality, the size, is 0. Then we're going to do public boolean member and then type D element, copying over the signature. And inside of this, we are checking if this element is, in our empty binary search tree. Well, our tree is empty, and so there's no way it could be inside of our tree because there's nothing in our tree, so we'll have to return false. Then our last method, which is going to be a public non-empty BST with type D add D element. This is the signature, and we need to make sure this is a lowercase e. And inside of this, we are just going to create a new non-empty binary search tree with the element. And that element is going to be the only thing that's inside of it, because if this method is called, it was called on an empty binary search tree, and so that means that now it's the only element that could possibly be in it because there was nothing in it before. So inside of here, we are going to return a non-empty BST, and in our constructor, we are just going to put the element. And of course, we need to say new, so everything is happy. And we haven't introduced D yet into our, things, and so we will come back to that, and this is just going to be an error for now. We have to add some stuff in here, and we said T here. This should be D. And we're going to have to do the same thing, extends comparable, and then this implements comparable. So now we are moving on to our non-empty BST, and it's not going to implement comparable, it's going to implement tree with our type D here. Now we need to add a constructor, and so we'll go public non-empty BST, and inside of this constructor, we are going to make sure we have a parameter for any elements that we want to add. So we will say type D element. That's how you construct things. You have to construct it with at least one element. And we also need to create some fields. There's a lot of stuff we have to create for our non-empty binary search tree. If you think of a non-empty binary search tree, what do you think of? Let's think of our properties first, not just jump into the code. And so our properties, well, we're going to have some kind of data, and that's going to be of type D, and so we'll say D data. And then we're also going to have a left and a right tree. And these could be empty binary search trees, or they could be non-empty. And so we are just going to call them tree left and tree data. Really tree right. Because we don't know if they're empty, non-empty, and that's why this interface comes in handy as well. And so our first thing, we have this element here. And so we are going to set the data to be data equals element, because that is the data that we have so far. And then our tree left and our tree right are just going to be empty BSTs. And so we'll say left is going to be a new empty BST, and then our right is also going to be a new empty BST. Now there's something I forgot here, and that's in our tree. We want to make sure these are full of type D so that everything in our tree is of the same data type. They're all ints, they're all strings, and that makes it a lot easier later on. And so here we will also have to say of type D to make everything happy, and we'll need to add a semicolon there instead of a colon. Now if we go back to here, our constructor is happy when we call it. So we're back here, we're still having errors because we haven't implemented all of the methods inside of our interface. And so we got to implement them. What was one? Well, we had public boolean is empty, and if it's a non-empty search tree, then obviously it is not empty, and so we will return false. Now cardinality, if we do public int cardinality, open close parentheses, open close curly brackets, here we're going to do something a little weird. It's going to be weird, get ready. We're going to do 1 plus left dot cardinality plus right dot cardinality. And we're going to open and close these parentheses, and we're actually going to return this. And so what does this even mean? Well, it means that this data is a thing, so we're going to add 1 to it. Then we need to check everything in the left tree. We need to add up all of that stuff, and then everything in the right tree, add up all of that stuff, and then once we have those answers, we can fill up those holes and then return our final cardinality. So if left is a non-empty binary search tree, then this will return 1. If it's an empty binary search tree, this left.cardinality will return 0. Now, if left is a non-empty binary search tree, then it's going to have some children that are probably not empty, and so then you'll have another 1 pop up in there. So this same method, if left, we say we do left.cardinality, then on the left tree, we are also going to call left.cardinality and right.cardinality on it. So say the left subtree of this thing has a right child but not a left child, then we'll get an added 1 with the left tree. We'll get a 0 for the left dot cardinality, and then we'll get a 1 for the right dot cardinality. This is a big concept. This is using recursion in our code, which we have not done very often here on 30 Days of Code, but it's super important. Next method, here we go. We are going to do more of this recursive stuff, so if you're a little shaky on it, do not worry. And so we are going to do public boolean member D element. And in this, creation thing, we are doing D because that's what we want our things to be a part of. So what do? Well, we'll have to check first if the root is equal to the element. So if root equals element, then we are going to want to return true, because that means it is equal to the thing. And here we don't call it root, we call it data. Makes sense? That is a big connection you need to make. The root here is the data. So it's obviously a member if the data equals the root. Otherwise, we need to check if it's in the left or the right subtrees. And so we can actually check these one at a time. We don't have to check both. And so if our element is less than our data, then we could just check the left subtree. So we could do left.member ELT. And if that's not true, then we'll check the right.member ELT. and then we will return this. Return. This is a big concept. And because we don't know that they're ints, we're going to have to do the dot compare to method. Compare to, here we go, to our data. If our element is less than our data, then this thing will be less than 0. And so we will go and search in our left subtree. Otherwise, we will go and search in our right subtree because our element is greater. Now for our last method here, we are going to do public non-empty BST with tatted type D inside of it, and we're going to add DELT. And so how do we add things correctly in our binary search tree? Well, we're going to want to make sure that whatever we insert, if we have our earlier example of 7, 8, 9, where 8 is the root and 7 is the left child, right is the 9 child, if we insert 5, then we want it to be a left subchild of 7 because it's less than 9 and it's also less than 7, and then that's it, so that's where we want to add it. And so we're going to say if root equals ELT, then that means it's already in the tree, and by root we mean data. And so if the data right here is equal to the element, then the element's already in the tree, so we can just return this. We don't need to add anything because it's already there. Otherwise, we need to check if the data and the element have a relationship with each other. So if the element dot compare to data is less than 0, then that means we should put it in the left subtree because the element is less than the data. So then we need to do return new non-empty BST, and we are going to want to return the BST with everything that we have so far plus our new element. So in our new non-empty BST, we are going to want this data here, but then we're also going to want to add the thing to our left subtree. And so we are going to want to do left.add ELT, and then we're going to want to keep the right subtree the same. We have not created a constructor yet for this, but we will in a second. And in the case where the element is greater than the data, then we want to put it in the right subtree. So we want to do return new non-empty BST data. Left will not touch, and the right.add element will be there for us to put in there. And so what constructor we need to add, we can go up here. We can say public non-empty BST, and we can have the D element be the data, and then we can have the left subtree, which is just going to be a tree of type data, and we'll put left tree here, and then tree of type data is going to be the right tree here. Then we'll add these great curly brackets, and we will say data equals element, the left equals the left tree, and we need to add that semicolon, and the right equals the right tree. And there we go. Now we have our new constructor, and it's great. And so we will go back down here, and that's it. We just implemented a tree data structure. We said we're going to have an interface tree, and we're going to have a class representing our non-empty, the things, our binary search trees with elements in them, and then we're going to have a class representing our empty binary search trees, which is amazing. So why am I telling you about these data structures? Yeah, we can represent them in code, but why are they useful? Well, they're extremely important in pathfinding and looking at relationships between things, algorithms. And this is like advanced stuff. This is kind of advanced for 30 days of code. I'm just trying to teach you how to code and make cool things. This is theory. This is out there. And yeah, you should probably know about it. And so what are these algorithms? Well, I'll show you like 2 or 3 examples because I know this is getting long. And you probably have better things to do than listen to me talk to my computer screen. And so one of the algorithms is breadth first search. And basically what it does is that given a set of data, it discovers each level first. And so say you have a tree with A as the root, then it'll discover A first, and it wants to find out like what is connected to A directly and indirectly. So say A has childs B, C, and D, and B is also, can go to B prime. Well, first it'll discover B, C, and D. It'll discover it's directly connected to those, and then it'll go and search in B and see, oh, I'm also connected to B prime. Another way you can do this algorithm is with depth first search, and basically what it does is it's the same idea, like what is A connected to in the world, and then you can ask questions like, oh, is it connected to this node? Oh, is it connected to this node? When you have like a billion nodes in your tree. And with this algorithm, you have the same tree, say, and you have A, and that has B, C, and D, and then B prime under B. It will go and it'll discover B, and then it'll discover B prime. So it'll go deeper in the tree first before going back up and seeing C and D and seeing what they're connected to. And so again, why are these important? Why does it matter what things are connected to? Well, you might want to see like, oh, is there a flight that goes from here to here? Oh, is there a road that goes from here to here? Oh, is it easy? Like, can you get by car to this city to this city? Stuff like that. And you can actually implement these like types of graphs with the data structures we've been talking about already. So remember our cues? Well, you can use those to implement breadth first search, and so discovering a level before you discover anything beneath that level. And for depth first search, you can use a stack or recursion to go deeper into the tree before you go back up. And again, there are a bunch of other algorithms that I haven't shown you today that use heaps, binary search trees, graphs, and other data structures, and they are super, super important to what you use every day in your real life. After 30 days of code, I will make a video about all of these algorithms because I need to remember them for coding interviews. But yeah, they're really cool. It's very theory-based. It's a little bit of coding, but it's more about what can you do with graphs, what can you say about them, that type of stuff. Yes, this was a hodgepodge of topics. We talked about heaps, we talked about the min heap, the max heap, the binary search tree. We coded our own binary search tree. And so that's it for this video. The HackerRank challenge is down below in the description, and if you have any questions, feel free to leave a comment on this video. I hope you learned something, and I will see you tomorrow.